A single horizontal force of P of 150 pounds magnitude is applied at the end of a lever. And determine the normal and shearing stresses on an element at point H, having both sides parallel to the x and the y axis, and also find the principal planes and the principal stresses at point H. So this is a little bit more complex of a problem because we have a couple things that we have to do before we get to the transformations. Specifically, what we have to do is we have to calculate out what the normal stress in the x and y is going to be, what the shear stress is going to be, and then we're going to use that information to feed into our regular plane stress equations. So how do we go about it? How do we attack this? Well, we got to do a couple things. First thing we have to do is determine an equivalent force couple system at the center of the transverse section passing through H. What does that mean? I have to find out what the moment there is. Once I find what the moment is, I can find out what the normal stress is. And so once I've got that, I can evaluate the normal and shearing stresses at point H. And then once we have that, and then we'll have everything that we need, we're just going to go right into our transformations, determine the principal planes, and calculate the principal stresses. So the first thing that we have to do is we have to come up with this system. So as I look at it, I'm looking at this element at point H, so I have to calculate things out. So we're going to start is we've got to do that force couple system. So I have that load P, so let's go back and look at this guy again. So since I'm trying to figure out what's going on here at H, I'm going to have to do a couple of different things. I'm going to have to calculate out what my force P is. I'm going to need to know what torque's on there. I'm going to need to know what moment is on there. So I've got a couple of different things going on. So if I'm doing a free body diagram of this, I'm going to have some force that opposes that P, because that's what's going to balance out. There's my sum of my forces in the Z direction. But then I've also got this thing that's wanting to spin around this way. So that also means that it's putting a torque on this. So in fact, if we move this P value over here, this P value is putting a torque right along this. And so it's torquing around that system. But because we have a difference of space to move this P value from here to here, there's also going to be a moment that's going to be resisting everything. So I've got to move all that stuff over to represent what's going on at point H. I'm going to need my force, which is P. I'm going to move that. That's going to give me a moment about Z, and it's going to give me a torque. And my torque's basically a moment about Y. This is kind of a three-dimensional problem, sort of. Everything's in one plane, but we've got to worry about all three axes, which makes this problem a little more interesting. And so basically, what do we have? Well, to move that force, first thing we've got is that force itself. And to move that force in equivalent system is I've got to worry about those two different values. And so the first one I've got is the torque itself. And so that torque, that force P along the x direction is put 18 inches out. So to get that torque, that's going to be P times 18 inches. And so once I do that, that's 2.7 kips per inch. Now, to move that force in the y direction from where it's being applied at D to where it's being applied at H, that was a 10-inch movement. So that moment about x is going to be P times 10 inches. And once we do that, that's going to give us 1.5 kips per inch. Kips times inch, kip inches. Okay, so now what do I have? So as I'm looking at this guy, I've got, here's my element, because I'm looking at this element here. So I have a normal force that's going to be applied by my bending. Actually, let me erase that because I did highlight the wrong part of it. It's this guy here. This is the plane element. So as I've got a bending force here, I'm going to have a normal force applied by my bending. So I'm going to calculate out the normal force. But then I've also got a shear force from this torque, and so I'm going to calculate out a shear force from that torque. So then this is where we're just going to pop into our equations. So my normal stress is going to be in the y direction, because our moment's rolling this way. And actually, no, it is this on the outside, because we wouldn't be calculating on the inside, because it would be kind of silly. So the moment is pushing up, is pulling it this way, so I've got a normal force, and that's going to be in the y direction. This torque is what's going to be my shear stress, because it's sliding along things. I'm going to have no normal force in the x direction, because I have nothing that is causing a force that way purely. I mean, I do have this torquing, but that's going to be a shear stress because it's sliding along. So how do I figure out the bending stress? Well, that's MCI. And so we calculated out the moment, 1.5 kip inches. And then we have C. If we go back to the geometry in the problem, which it tells me my diameter is 1.2 inches. So that means C is 0.6 inches. And then we divide it by I. What's I going to be? Well, that's going to be pi over 4 times 0.6 inches. All that raised to the fourth. That's going to give me a Y stress of 8.84 KSI. Okay, now let's look at our shear stress, because our shear stress is going to be given by TC over J. So we calculated our torque, 2.7 kip inches. Once again, we know what our C is 0.6 inches. Now we have J. J is different than I. It's actually only pi over 2. I don't know why it keeps spiking that. Pi over 2, 0.6 inches squared. And so we calculate out the shear stress, and then we're going to get 7.96 KSI, all positive. And as we said, as we look at this, there's nothing driving the x direction stress, so the stress in the x direction is going to be 0. Okay, at this point, all the tricky stuff is now done, because now we've converted our three-dimensional object into our state of plane strain, plane stress. And so the last thing to do is let's actually calculate it out. So this is just, I've rewritten my stresses as a plane element. 8.84 KSI in the y, positive shear stress, and now I have nothing in the x. So let's determine the principal stresses and strains. Principal stresses and principal axes. So tangent of 2 theta p is going to be equal to our normal equation, which is 2 times the shear stress divided by sigma x minus sigma y. So 2 times 7.96 KSI divided by 0 minus 8.84. Once again, I'm leaving the units out of here because they're all KSI, so I know they're all going to work out. Negative 1.8. So what I'm going to do is I'll take the arctangent of that. So 2 theta p is going to be equal to negative 61 degrees and 119 degrees. So that means that my principal angles are going to be negative 30.5 degrees and 59.5 degrees. You know, one thing that probably didn't bring up in the lecture is, what is a negative principal angle? Well, negative would be going clockwise, because counterclockwise is always positive. So negative 30 degrees means that we're going to rotate clockwise 30 degrees to get to the principal axis. Okay. So our principals 1 and 2 are going to be equal to our average stress plus or minus the square root of the difference in our stresses divided by 2 squared plus tau xy squared. And from there, just plug in our numbers. 0 plus 8.84 divided by 2 plus or minus 0 minus 8.84 divided by 2 squared. This is kind of the reason why you use a lot of the differences squares, so you get a negative number and it becomes positive and doesn't blow up the entire equation. 7.96 squared. And so I plug all those together, and I'm going to get principal 1 and 2 of 13.52 KSI and negative 4.68 KSI. And so obviously that first principal stress is going to be at that first principal angle. So that 13.52 KSI is going to be at negative 30 degrees. In fact, here's a little picture of that. And so there we go. The real fun part of this problem is that entire first part of taking that three-dimensional stress state and bringing it down to basically almost like a puzzle, figuring out what the normal and the shear stresses on that plane element are.